right, chugging along with relative motion. One last thing for you to consider. This is now our fourth, unless I've had to add things, this is our fourth little video clip. We're going to run with the same setup. Albert's hanging out on the ground, not moving. Isaac is hanging out on the paper. He does what the paper does. We're going to go with a number of 2. And we've got our little toy car. We're going to also say that it's moving at 2. We haven't really talked about units in the videos. We'll say that these represent 2 kilometers per hour. We'll come back to units after. What we've got so far is if the 2's are in the same direction, they combine to make a bigger number. 2 and the 2 would add up to see a 4. If we flip it, so the 2's and the 2's are in the opposite direction, they add to make a smaller number. In this case, 2 and 2 add to make 0. So really we've got a new cool math thing that I'll come back to when we start taking notes, and there's different ways to add numbers. Sometimes 2 and 2 add up to make something bigger. 2 and 2 could add up to make something as big as 4. But sometimes in physics, 2 and 2 add up to make something smaller. In this case, 2 and 2 could add up to make 0 because of that direction part. Directions are going to become very important. Okay, the last piece, if this is making sense, when the cars are going in the same direction, we added the 2 and added the 2, they combine to make 4. When the cars are going in opposite directions, we added the 2 and we added the 2, they happen to make a 0. The last case, and really the cool application like pilots and people that are involved in sailing boats or big ships in moving water, what if they're not in the same line? The 2 and the 2 in the same direction made a 4. The 2 and the 2 in the opposite directions, 2 and the 2 in the opposite directions made a 0. What if I give you something totally weird? What if the car's going sideways as the paper's moving? So I'm going to set up one more. The car's going to come towards me, towards the bottom of the screen at a speed of 2. I'm going to shove the paper to the right. I'm going to try and get the same speed, a speed of 2. What does everybody see? What does Isaac see the car doing? What does Albert see Isaac doing? And then the money maker, what does Albert see the car doing? So paper going to the right at 2, car coming towards the bottom of the screen at 2. You guys are like Albert. What do you think you're going to see? Okay, I'll set this up, and once the car's on the paper, I'll start sliding the paper. Alright, did you see what you thought you were going to see? The math is going to get a little bit harder. Let me grab a marker. When, you'll get 2 markers. When the car was going forward at a speed of 2, and the paper was going in the same direction at a speed of 2, we could add those and say that 2 plus 2 equals 4. When we had them go in opposite directions, when the car was going, let's say the car is going this way at a speed of 2, when the paper is going this way at a speed of 2, we still add them, but in this case the 2 plus the other 2, they combine to make an overall speed of 0. We'll come back to it in our notes and things, but this is almost like saying 2 plus negative 2 combine to make a 0. This visual of thinking of the speeds as arrows is going to be hugely important. We're going to come back to that as well. We drew the one speed, we drew the other speed, we drew the one representation. I'm going to use other words soon. We drew the other one in a representation to get a visual of how they combine. The same method, we drew one as an arrow, drew the other as an arrow, get a visual of how they combine. That tool we can use for this last case when the car was going sideways compared to the paper. We drew one. Let's say this represents the paper. It was going sideways at a speed of 2. The car happened to be coming down at a speed of 2. This combines to make what we saw is this car moving on a funny diagonal. That's what Albert saw. That's what you should have seen on the camera, is the toy car should have tracked on an angle across the paper. Coming out of grade 10 math, we can maybe go one step farther. I'm not huge on memorizing vocabulary, but this kind of triangle with a 2 and a 2, we would call that isosceles. Because this angle up here is 90, the car was driving the paper was moving sideways, the car was going down. There's a 90 in that part of the triangle. Through a little bit of logic and maybe, well, it's been a long time since some of you have had to do math. This angle down here, in here, without doing SOHCAHTOA, I know that that's 45 degrees. Because it's an isosceles and a 90 on one side, the other two have to add a 90, so 40, 40, 45 and 45, that works out to be a 180 inside angle. That tells us the direction that the car is going. If I actually want to know how fast the car is going, I'm just going to call it speed for now, but we'll learn some. If we haven't got there in our notes yet, we'll get a better word for that. To get the speed, we need to do Pythagorean theorem. How fast the car is going is represented by this hypotenuse side. Down here is represented by the long straight blue line. In this case, they cancel each other out. There really was no line by the time we combine them. So this ends up being whatever, 2 squared is 4, another 4, ends up being the square root of 8. If it was a square root of 9, the answer is going to be exactly 3. We're a little bit less than 9, so we're going to be 2 point something. I forgot a calculator, so I don't have all the exact decimals. You can crank that one out. That is where we'll pause and work through some paperwork, but that's really the guts of relative motion.